And in this section here, we're going to be talking about we're going to be talking about area, but in this particular case here, we're just going to be approximating the area. And I'm going to run a simulation, and we're going to use a limit to find the exact area. So it's going to be interesting. First thing I guess I need to do here is draw us a picture so you get an idea of what is going on. Let's make our curve, let's see, I don't know, we'll pick this color here. And we are going from 0 to 2. So something like that. What we're looking for here is we want to find the area under this curve. And we're going to start off by approximating the area, and we're going to be doing what's called using the right endpoints. And I'm going to divide this box up into 5 pieces. So in other words, each interval right here is going to be 2/5. I'm going to let I be box number 1, 2, 3, 4, and 5. Alright. And what we're going to want to do here is, of course my picture's not going to be perfect. So this first, I should not call them boxes but rectangles. We're going to come out 2/5. And this right endpoint is actually intersecting with the curve. To actually find that point on the curve, we would find f, or find the value, you'd find f of 2/5. Now of course our function, remember, is negative x squared plus 6. Negative x squared plus 6. So if we wanted to find the y value, we would plug 2/5 into the function here to get the y value. And then of course we come over, so this would be the second I. So in order to find this number right here, this is going to end up being, so this becomes 2/5 times 2, which is 4/5. As we continue these rectangles, what we want to do is find the area of each one of the rectangles and then just sum the area up. So for example, this rectangle right here, to find the area, we're going to take the width, which is 2/5, and multiply it by the height, which is going to be f of 2/5. So as you can see, so this is the width and this is the height, and height times width gives us the area of the rectangle. Well, if we did that for all of them, this would be f. So the next one we said was going to be 4/5, and its times 2/5 also, because its width is staying the same, plus f of, and then of course what we're doing here is taking 2/5 timesing it by I. So 2/5 times it by 2, and then 2/5 times it by 3. So that's going to end up being at 6/5, right? Times 2/5 plus f of, and then of course we go to 4, and that's going to be 8/5. I need to try writing a little neater. It looks to me like I get in a hurry. So this was I was 1, I is 2, I is 3, I is going to be 4 this time, and that means 2 times is 8/5. So we'll write 8/5 in here, times that by 2/5, plus f of, and of course now we're doing 5 finally, and that's going to be 10/5. And of course we can reduce that down, but we'll leave it like that. Times 2/5. And of course we could factor out the 2/5 all the way out and then sum that up. But remember, in the previous section we talked about a shorter way of writing this, and that is the sum. I don't know what happened there. We have the sum of I going from 1 to 5, and it's f, and each width of the interval is 2/5 I, and times 2/5. Okay. So remember, this is the height and this is the actual width here of the interval. Now what I'm going to go ahead and do now is I'm going to go ahead and take this and plug this 2/5 I actually into our function. So we end up having the sum of I going from 1 to 5 of negative, we have 2/5 I squared plus 6, and I'll just put a bracket around this, and of course times 2/5. So as you can see here, this is our function. This is f of, well, I should say f of 2/5 I here. Alright, so this piece right here is our f of 2/5 I. Well, in the previous section we talked quite a bit about the summation and some formulas, and I'm going to go ahead and break this up and show you how to actually calculate this using some of our previous formulas. So I guess I should write equal sign here. I equals 1 to 5, and I'm going to distribute this 2/5 across each one of these here. So this becomes negative 2/5, and then this is 2/5 I quantity squared, plus, now you see I'm separating this because we have an addition sign here, and we have I equals 1 to 5, and of course taking the 2/5 and multiplying it by 6, so that ends up giving us 12/5. So we've now broke it up, and let's continue to break this piece up here. So this becomes 2 squared and 5 squared, so this becomes 4 over 25, and then I squared, and of course 4 over 25, you multiply the 4 times, well, I guess I better not skip any steps here. So we have negative 2 times 5, and remember we can take this negative 2 and bring it out front, but I'll do that here in a minute. 4 over 25, and then I squared. plus, and I'm just going to rewrite this one here. We can go ahead and take this 8 over 125 and bring it out in front, so negative 8 over 125 I equals 1 to 5 of I squared. Now you're going to have to remember the formula we used for summing up I squared. We're going to use that formula. And I'm going to just put a big parentheses right here around this. I'm going to write this with an n, so you can see the formula. It was n times n plus 1 times 2 to the n plus 1, and it was all over 6 plus, and then this one here is going to end up being 12/5 times 5. And in this particular case, we're going to say, of course, n up here is 5. So you would plug 5 into this piece right here, and this would give you the actual sum of all of the boxes if you plugged that in. And that sum actually is, so this should equal 212 over 25, which is approximately, trying to remember, but I think it was like approximately 8.48 or something like that. 8.48. Okay, we'll just round 2 decimal places. But here's the question. Up here in the very beginning, what happens when we've got 2/5? We're letting each one of these, the width of each box to be 2 over 5. But what happens when this bottom piece right here, so let's say that this is, I'll just rewrite, this is 2 over, let's say, k. But what happens when k goes to infinity? Well, that means that there's just going to be more boxes, and of course the more boxes there are, the less, you see this little empty space right here, that empty space is going to converge to 0, right? So the smaller the boxes, we're going to get the actual theoretical value between 0 and 2. And what I'm going to do here is I'm going to set up a limit. We're going to set up a limit. So in other words, if I said the sum, and I'm not going to work this out, I'm going to let you work this out. I equals 1 to k of f of 2k of I times 2 over k. Right? So what you need to do is go through the exact same process and work this out, and then when you get down to the bottom of it, okay, to the very far end I should say, what you're going to want to do, you'll have everything in terms of k, and what you're going to want to do then is take the limit as k goes to infinity of this, right? Take the limit as k goes into infinity. Once you get this worked out, everything should be in terms of k. So I'm going to go ahead and write out actually what this is equal to here, but I'm going to write it down here. So you need to try to work this out and get the same thing that I get. So this should be negative 8 over k raised to the third power, and then I'm going to do this here, k times k plus 1 times 2k plus 1. That's all over 6. Put a bracket around that, and then we have plus 12 out here. Plus 12, and I don't know, we'll put a parentheses around everything. This limit is when you take the limit of this. Okay, so you're going to have to do a little working out there. And I've got a section on limits. So when you get this all worked out, this should equal 28 over 3, which is, thinking, let's see, 28 over 3, that's like approximately, it's approximately like 9.33. Now what I've done here is I wrote a short program in Python, and we're going to shoot out some values when k is 1, 2, 3, 4, and up to 5. No, actually we're going to go to a big number. We're going to try to approach this 9.33. Alright, I was barely able to get everything on the screen. Anyway, this is written in Python. This down here is that is the what the limit, remember, is the limit as k goes to infinity. And in this particular case, I'm letting my k be c. So c is going to increase, and of course we're going to go to 1,000 because we're going to try to approach that 9.33. I don't think we're going to get there, but anyway, and of course it barely ends with the parentheses here. So this is code written in Python. I highly suggest you get involved with some programming if you're going to be studying math, or hell, I guess just about anything else. You can go to the Python website, download their software, and anyway, I'll copy and paste this right below the video where you can get it. Now actually I think what I'm going to do here is we're going to go to 5. So let's see, you gotta run, then you gotta save it. Okay, these are some values actually from, I just ran this code a little while ago, checking it out. Alright, let's, well, it's down below. Okay, so if we only had one rectangle, we'd get a 4. 2 rectangles, you would get 7. 3 rectangles, 4 rectangles, and of course this is the one we calculated earlier, was 5 rectangles, which was approximately 8.48. Now let's do a bunch of rectangles and see what this thing converges towards. So I'm going to go up here in the code, change this to 1,000. Now what we're going to see is a big bunch of scrolling numbers. So remember, this is when k, as you can see over here, this is k, so the number of rectangles are increasing, and this would be the approximate area actually under the curve. I've got 30 more seconds in this video, and let's see how close we could possibly get. So right now we're at 9.31. Now I'll just tell you that the theoretical value is 28 over 3. Of course that was something we just calculated by actually doing the limit. So if you actually forgot your calculus, and I think we're going to run out of time here because I'm going to end this video here in a few seconds, but as you can see, it's converted